In this video, we're going to discuss classic operating systems functionalities, including virtualization of CPU and memory and concurrency. So let's start with what is virtualization. When we virtualize something, we are creating an illusion that each program we have existing in memory has sole access to that memory and sole access to the CPU and sole access to whatever other resources it needs. But typically, that is not the case. In order to make multiple programs run on a machine, not all of them can be running at the same time. We start one process, we take that process off of the CPU, and then we put a different process onto the CPU. Even on a single core machine, we can have multiple programs that are making progress. Another form of virtualization is when we log into a Linux machine or a server in the cloud, and we assume that our access to that machine is not going to be impacted by anybody else also trying to log in to the same machine. We believe that we have sole access to the machine and do not care how anybody else happens to be using it at that point in time. So when you write a program, you're not going to worry about what other programs might be running at the same time on that machine, and you're not going to typically worry about what other needs those programs have. So when we talk about virtualization in the next few videos, we will be discussing how to run multiple programs on a CPU that executes instructions sequentially. When we can't execute them at the same time, we can only make sure that each is making progress. Virtualization provides an illusion to a program that it has exclusive use of the CPU and memory and disk, even though these things are actually being shared by multiple different programs. Virtualization is actually an incredibly difficult task. It is half a semester's worth of work to be able to understand how everything comes together. When we virtualize memory, we are talking about creating this illusion that each individual program has its own memory and that no other programs exist inside of memory. The reason why this is difficult is because the way that we actually implement this is by assigning each individual program its own address space in memory. But the operating system and the hardware have to work hard to make sure that the programs don't really need to know where it is that they are located. Now let's talk about concurrency. Concurrency, when defined, is the act of interleaving accesses to resources. For instance, when we're talking about CPU, we would say that multiple programs may be able to concurrently make progress by accessing the CPU, but it's not the case that those instructions are all happening at the same time. We are interleaving the instructions from multiple different processes by allowing a program to run for a little bit and then taking it off the CPU to put a different process onto the CPU. As long as we are careful about how often we do this context switch, we will still be able to make progress on all of the scheduled processes. So here's an example. Let's say that we have a bank transfer program and we are going to send money to two different individuals. In this case, we'd say that user one has $100 in their balance. So we're going to send a transfer from user one to user two for $70 and a second transfer from user one to user three for $80. These are both executing concurrently. We don't have $150 in that account. One of these should fail, but when we execute instructions from multiple streams of execution concurrently, there is not a guarantee on what order those instructions are going to execute. So if we check that the balance is greater than or equal to 70 for the first transaction, and then immediately switch over to the if statement for checking if the balance is greater than or equal to 80, the interleaving programs will allow the balance to be subtracted by 70 first and then subtracted by 80, resulting in an end balance for user one of negative $50, which should not have happened. This would not be a correct version of running this program because we would want one of these transactions to fail if there is not enough money in the account. So this results in us needing to have additional mechanisms that control for grouping pieces of code that really ought to be run together without having any kind of context switch in the middle.